For SMTP, for instance, it does the hello verb or the EHLL verb, and you can fuzz any protocol that has certain decisions like that that may or may not be the same. We walk down every path and do every single one individually. Okay. The other thing that we have is code coverage. We are in process because we're utilizing PyDebug, so we're actually attached to the process that you're dealing with. So we can do things like code coverage. And most fuzzers out there, they don't actually do anything like that. So you could be sending 500 test cases that go down the exact same path, which is fairly useless, whereas we can tell you when you're going to be splitting off from that path, why you split off from that path, which primitive was being fuzzed at the time that you did split off of that path, so you can kind of have a better idea of the protocol without having to reverse the whole thing out. Yeah, we use PyMay for that, which does regular. You can do step-by-step instructions, or you can do MSR-based code coverage, which is just basic block by basic block. And because we're in process, we can do things like detect access violations, detect null pointer dereferences. We can do a bunch of things like that. Most of the fuzzers out there, like Codenomicon, it'll generate the data, send it over, and, well, you have no idea if something bad actually did happen. You just kind of wait and hope. Different approach, like Mu and Breaking Point, is they'll just cycle the device that they're actually fuzzing. So if they're fuzzing a switch or a router or something like that and it stops responding, they can actually just completely cut the power and start it back up. So we have something similar to that. Because we have a process monitor attached and we're using PyDebug, we can catch any exception that occurs, figure out what type of exception it is, dump context data, tell you, I mean, it's very easy at a glance to tell if something is going to be a null pointer deref or something that's going to be more interesting than that. We dump the SEH chain, all sorts of things like that. And if a crash does occur, we have another concept of, well, we have the process monitor itself is what we call an agent. And we have a few of those. Another one is the VM control agent. And that one monitors the VMware instance that you're running, if you're running it in that situation, so that if the process monitor agent detects a fault, it notifies the VMware agent, which can reset to a snapshot where things are running okay, which we're going to demo later. Another problem with a lot of the fuzzers out there are going to be the amount of time it takes to actually understand the protocol, get your fuzzer written, and just get to work on it. So we have a few utilities that remedy that, like a PDML parser. PDML is a packet descriptor meta language, I think, and it's a format that Wireshark and other sniffers can output sniff data to. So it's just an XML format, and we have a little parser that will just run through that and give you all the Sully primitives and a complete request that you're going to have to probably go through it by hand and trim a little bit, but it'll save you a lot of time. Because Sully is very modularized, you can have many people working on different aspects of it at the same time. Yeah, so it's definitely just, we have a few utilities, obviously, for doing that kind of stuff. It just makes it a lot easier than the current things that are out there. Now we're going to go into architecture. Pedram's going to cover that.
So this massive diagram seems a lot more complicated than it really is, and we're going to kind of zoom into the different portions to describe what everything does. But in essence, this is like the high-level overview of how Sully works, and, how it's all the components, how it's made up. So this gray shaded area where it says user developed, if you're building a fuzzer, that's really all you have to worry about is that small portion of it. The rest of it is if you want to actually extend the framework, creating a new agent, writing new utilities, whatever. So we have this data generation piece. We've got these primitives that we're going to walk through, and Legos, which are our word for custom-built complex types. We've got blocks, and we have utilities, so stored encoders, and all the stuff we'll get into. And from there, these all go into a request library. So you will write a request, store it in the library, and then pull them together in a script that you're going to write called a driver. That's when you build this graph relationship between these requests. The session management component is what's actually going to walk this graph and do all the fuzzing for you. The file system is where the crash bins, packet captures, session data gets stored to. We've got command line utilities that are kind of like their own little piece, and various agents that are responsible for instrumentation, monitoring, things of that nature. And then I've got this little HTTP icon to kind of demonstrate that your driver, because it uses the session class, has this built-in web interface. So there's these four major components, right? You build these requests out of primitives and Legos. You have these requests chained together in a session. You tie them all together, targets, agents, and requests in a driver. And like all these words in red are Sully speak. They all kind of make sense, but they're highlighted just so you know what the variables and functions will be called. So general usage, how would you use this outside of this talk, you don't care about how it works. You just want to use a fuzzer. And it's pretty simple. You sniff some traffic or you verse a protocol, and you break it down to these individual requests. So in the case of SMTP, which I'll be using again later, you might have a hello request, a mail from request, a recipient to request. You represent all these in this block format, tie them together in a session, and then just say fuzz and review the results. The rest of it is all automated and taken care of for you. So drilling down to this graph, this data generation piece, with the overview, Attell really had it right. His block-based approach for protocol representation is really simple. It's extremely powerful. You can pretty much represent everything or any individual request in this block-based format. The kind of things you can't do, like deal with challenge response and what we call previous packet specify size, those are taken care of in the session layer. And so, these protocols that you represent as primitives, blocks and block helpers, they all have these optional arguments. And for example, one of them that's common across the board is the name optional argument. This is going to give you direct access to a primitive instead of having to walk the block stack to get to it. And you can see, this is probably a good time as any to kind of pull up the epidoc documentation. But we have these docs. It's pretty extensive. It comes with it. It's just to kind of prove to you that we spend a lot of time documenting. It's going to be a good read. And then, of course, you've got the epidoc generated stuff. So if you want to know, for example, what optional arguments a certain primitive takes, it's really easy to do that. Come to primitives. I want to look at, whatever, a group. And then you can come down here and see all the arguments, optional arguments, and the kind of helper text that you've written. And finally, every request is going to start off with sinitialize. And we're going to start stepping through the different API that you're going to be calling to build out these requests. So static.
All right, so I'm going to go through some of the actual primitives, which are the simplest types that you're going to be using to define the request you're dealing with. First one we're going to go through is static, which is pretty self-explanatory. It has aliases, deno, raw, unknown, things like that. And you basically can give it just a string of whatever static data you want. Binary we kind of took away from Spike, which is you can do similar things, but you can represent the data in all sorts of different forms, as you can see up there. Another one we have is the random primitive. The random primitive is the only one that doesn't have a set library of values. It is actually done heuristically, so it generates random data every time you're going to instantiate it. And you have different arguments to control how it's going to do that, the minimum length, the maximum length, the actual number of mutations that you want to deal with, and things like that.
I got it. Integer primitives, simple fields for like a character, a short, long, D words. And there's convenience aliases just like with the sdeno, s unknown. And so, like he mentioned, all of our primitives are based off of a fuzz library, a set of heuristical values just chosen that may cause a fault. So one of the optional arguments for an integer is that you can turn on full range, where it'll go, for example, in a short, it'll go through all 65,000 plus options. So let me pull up the source code real quick. Here is primitives. All right, let me pull up int. All right. So for example, anytime you instantiate an integer, we're not going to cycle through every single value by default, because that's going to, the combinatorial explosion that's going to occur there is just going to take forever for your fuzzer to finish. You can turn it on if you want, but by default, we try and keep things, same values. And so here are the kind of the areas that we choose. We're choosing integer boundaries that might be interesting. So 0 and max known are obviously interesting boundaries for any size integer. Or divided by 2, divided by 3, divided by 4. And this add integer boundary is going to do plus and minus 10 from each one of those sections. So if you have something like a heap allocation that's going to occur off of a integer field in a protocol, and the math on that's going to be like a +1, we'll catch that wrap. Or if it's going to be like, times 8, because that's the size of some structure, +5, we'll catch that as well. So it's just some integer heuristics to put in there so that you don't have to go through this full range of values to fuzz. Other things you can do with the integer primitive, it supports ASCII, so if you're doing like a content length in a HTTP post, you can render it ASCII. Or if you want to render as binary, you can render as binary. You can do signed or unsigned. They'll throw a negative sign in there in the case of ASCII.
So the next one we have is the string primitive. The string has all sorts of different options that you can have, static sizings, paddings, all sorts of things like that. It also has a fuzz library similar to integers, which I'll pull up in a sec. Another thing that we have are delimiters. So we have strings, which is just, you're going to give it a default value. That's the only thing that's required. After that, it's going to go through the fuzz library and just linearly replace with all the different values that we have. I'm going to pull that up now. And you can see we'll take the actual value that you provide as a default value, repeat that a certain amount of times. We'll do things for UTF specifics. We'll do things for format strings. Just a lot of different things that we've encountered that will cause problems. We've ripped examples from Codenomicon, from Spike, things like that. All sorts of different problematic strings, basically. So we have a little example here, which is just going to show an HTML tag. The first thing that we start with is a delimiter. So delimiters are basically like strings, except that we have specific ways that we're going to mutate those. Sometimes we'll just take out the delimiter. Sometimes we'll do directory traversal kind of things. We'll do a lot of white space, all the different problems that generally arise from delimiters themselves. So in this example, we declared delimiter, which is just a bracket, a string for body, and you can see it's just an HTML tag, basically, comprised just of strings and delimiters.
Blocks, so this is where, you take all these basic primitives and you put them in blocks and you nest blocks, and this is how you really build a complex protocol. So if you're familiar with Spike, this is very similar to you. If you're not, this is new stuff. So we can take a block, instantiate one, and just put whatever primitives we want in there. And blocks are opened with sBlockStart, closed with sBlockEnd, and both these functions return true by default. So in Python, if you want to just tab it out so it looks nice, you can do that. And then what you can do with blocks is you can associate them with a group, an encoder, a dependency. And these are some of the more advanced features of our data representation that kind of takes it above and beyond what Spike and others could do. So if you have like a scale of 1 to 10 of like shitty fuzzer or perfect fuzzer, maybe in the data generation world, the current fuzzing technologists take it to like, a 5 or a 6. And so we're hoping that Sully takes it to like a 7 or an 8. But on the other aspect of the world where it's like monitoring, automation, the other portions of fuzzers, maybe the fuzzers available today take it to like a 1, and we're hoping that we'll shoot that up to like a 5 or a 6.
So the next part we're going to talk about is groups, which is another similar thing to primitives. A group is basically going to be a list of specific values that you want. The example we use here is HTTP verbs. So if you're doing get, head, post, trace, things like that, you can actually create a block and have it start with a group, and that group is going to iterate through each one of those things. So, for instance, if you have a block that has 2 strings, it's going to have the number of mutations that a string has is about 1,000 in our fuzz library. So you multiply that by 2, and your block itself has 2,000 different mutations. So if you're going to prepend that with a group, such as a get, head, or in our example, we're using get, head, post, trace. That's 4 different verbs. So the amount of mutations you just basically multiply it by the number of items in the group. So 2,000 times 4 is going to give you the amount of mutations that specific block has. So it'll change it, mutate everything within it, finish that mutation, and then go to the next in the group and continue in that fashion.
An encoder is a really simple concept, but it's extremely powerful. And an encoder is how we actually do things like if you want to fuzz DC RPC, or Ganesh, who's talking at DEF CON, if you want to fuzz SCADA even, DMP3 protocol, like you can do that with Sully because of this simple concept, which really adds a lot of power. So all it is a block modifier. And what we're doing is we're going to connect a function to any given block. And so when that block is finished rendering, it's mutated, it's rendered as contents, those contents then go through this extra channel, through this function that you add, and that's what actually goes out onto the wire. So you can represent your data normally, and then if it's, for example, zlib compressed, you just attach one encoder to it, and it will generate the protocol, validly. And so in the case I give here, this is a real-world example. It's not the trend demo I'm going to give. It's another trend target.